Now we've got Bruno Moorthamers. Bruno now works for Dart Corporation in Kansas. And Bruno was a PhD student, worked on this project for 4 years, 3 years, 3.5 years, something like that. Anyway, thanks for joining us, Bruno.
Yes, can everyone hear me?
Yep.
All right, let me quickly share my screen here. I selected a few slides from two of my, from my dissertation and then from a paper I presented on the accuracy of Küchelmann's analytic derivation. And then my dissertation was on a study of variable sweep profiles. I'm going to try and go to some of these a little quickly because I see we're already pretty far behind. So I'm sure this is maybe already covered by some of the other people, but so the reason why we were interested in morphing wings was because we can do directional stability control using variable camber compliant main wing and get rid of the vertical tail, which would lower radar signature and drag. This obviously opens up the design space to a lot of new possible design configurations. So that necessitated the need of a low resource aerodynamic analysis tool. So we obviously have mockup, which is a numerical lifting line method. But as you'll see later, I believe Jackson and Corey will probably talk about this. It doesn't, the classical way did not really work for swept wing design. Because the bound vorticity is placed along the quarter chord line, and that discontinuity in the middle at the root causes excessively strong downwash in the root region, and so doesn't predict lift and drag very well. I was part of like an effort to make this work for swept wings, and one possible solution that Warren Phillips suggested was placing the bound vorticity along the locus of section aerodynamic centers. So the aerodynamic center is the point along an airfoil where the pitching moment does not change with angle of attack. And he theorized that placing the vorticity along the line, the span-wise line that would connect all these points, that would improve numerical lifting line for swept wings. Now, Küchelmann has an analytic approximation for this locus, for this line. And so Phillips was already interested in this and compared this approximation to a few wind tunnel data that he found. And those are the 4 wings that you see here. So the dots are experimental calculations or measurements basically of the aerodynamic center. And that dashed line is Küchelmann's analytic solution. And so that looks promising, but in order to get a better understanding, we wanted to make sure that Küchelmann's analytic solution was well suited over a wider range of wing designs. So I started with generating more comparison data using a panel method. I'm not going to go into these equations. That's not useful. But what I wanted to point out is that Küchelmann said that the aerodynamic center is only at the quarter chord. So like classical numerical lifting line says, for a large portion of wings with high aspect ratio. But disturbances at the wing tip and in the wing root means that the line of vorticity never reaches the line of geometric sweep. So if we go back to the previous slide, you see how this dashed line curves backwards at the wing root and curves forward a little bit at the wing tip. So that's because of the disturbances in those regions. So he came up with an effective sweep angle. And what I just want to point out is that this is a function of aspect ratio and section lift curve slope. So CL alpha here and RA is aspect ratio. Yeah, this is for finite wings basically because aspect ratio is in it. And then this is his solution for the aerodynamic center position as a function of the span-wise position. So again, don't pay too much attention to this big equation. The point I want to make is that his solution is dependent on spanwise position, aspect ratio, lift curve slope, and that effective sweep angle that he came up with. So those are the main variables that will affect his solution. So before I generated a bunch of data for a large set of elliptic wing designs, I looked at two specifically. One of them has aspect ratio 2 and no sweep, and the other one has aspect ratio 8 and 20 degrees of sweep. By the way, at this point in my research, I only looked at elliptic wing designs. That was because at that point, there was a limitation of the panel code I was working with. So here are these two wings, and I just want you to look at the figures. So on the left, we have, by the way, the wings are normalized on the horizontal axis. That's why they look so stubby. But on the left, we have that unswept wing of aspect ratio 2, and the little dots are the numerical solution that I came up with the panel code, which in this case was Panair. And the solid line is Kuckerman's analytic solution. So it looks quite nice visually. And on the right, we have that aspect ratio 8 wing with 20 degrees of sweep. And you don't even see the solid line because it really lies right under all these dots here. So from a first glance, it looks as if Kuckerman's analytic solution matches quite well with the numerical data that we generated. This was for a NACA 0012, so 12% thickness profile. I did the same thing for 4 other thicknesses, so 12% to 21%. And you can dive into the legend if you want, but the conclusion is that it even captures thickness effects quite well because it follows these trends for the different thicknesses quite well. On the left, we have a magnified view of the root region. So you see this curving aft. And on the right, we see a magnified view of the tip. You don't really see this curving forward that you saw on those figures from Phillips, but that's because this is an elliptic wing. So the chord comes to 0, so it has to go there. We talk about the accuracy of Kuckerman in terms of its difference from the numerical data. So the shift of that locus from Kuckerman's solution, the difference of that with respect to the position of the numerical data. So that shift is just the difference between the two results, really. And we call it delta XAC. And so, sorry, this is a shift from a 2-dimensional solution. I'm gonna skip over this slide. I forgot to include some extra information there. The point is that I looked at a large set of wing designs from aspect ratio 2 to 30, from negative 40 degrees of sweep, so forward sweep, to positive 40 degrees of sweep, and those 4 different thicknesses that I mentioned. And I looked at the root mean square error of all these wings between the analytic solution from Kuckerman and the numerical solution from Panair. So that delta XAC between Kuckerman and Panair, I took the root mean square of that over the whole span. And the conclusion is that it is low for all of these wings. So here you see 0.01, and most of the wing designs on the horizontal axis, we have all these aspect ratios. All these different lines are for different rearward sweep angles in this case. And almost all of them fall below 1%. So in the order of magnitude of accuracy of lifting line, this is pretty good. So the conclusion of that is that Kuckerman's solution is pretty accurate, and it's a quick way of predicting the locus of section aerodynamic centers compared to our numerical data from Panair. So like I said, it stayed below 1% for majority of rearward swept wings. I didn't show you the results for forward swept wings, but it stayed below 3% there. And so the end of this study was to then recommend this locus, like Phillips suggested, for placing the bound vorticity on a numerical lifting line, and that I believe either Jackson or Corey will elaborate on, but the conclusion is that it didn't necessarily solve everything for swept wings. The second part of my presentation is going on the variable sweep profiles. So obviously in aircrafts, our swept wing lines, for example, the leading edge or the trailing edge, are often straight lines. This is mostly due to manufacturing reasons. But in nature, we don't really see any straight lines. We often see a variable sweep profile where the sweep angle varies across the span. So here you see it across these bird's wings or fish tail fins. And kind of the question I wanted to answer is are those curved sweep profiles more efficient than wings of constant sweep? So I introduced the term crescent wing. And generally, a crescent wing is just to be understood to be half moon shaped, a crescent half moon. It's in the name. My definition of crescent wing is a wing with linear sweep. So this means that the sweep increases from 0 at the wing root to a finite value at the wing tip, and I call that value lambda tip. And so between 0 and that value, the local sweep along the span increases linearly. And again, I looked at a wide range of wings, this time using Flightstream, which is a much more modern panel code than Panair, so it did not have limitations of needing elliptic wings. Taper ratio, I varied from 0.25 to 1, aspect ratio from 4 to 20, tip sweep from 0 to 40. So I ran all this big design space using constant sweep profiles. So constant sweep profile is what you know as a regular swept wing, and linear sweep profile, which are those crescent wings. They all were analyzed at angle of attack of 5 degrees, no twist, double a 12th profile, and the total was about 3,000 wings that I analyzed with Flightstream. I looked at a few different things, but for this presentation, I only picked out 2, which was a measure for induced drag. So kappa D is a term you can devise from the equation for induced drag. And really it is a measure for how far a particular wing deviates, or the induced drag deviates from the elliptic lift distribution. And then I came up with the term kappa AC, which is again a shift in aerodynamic center, and this time it's not the locus, it is just the global aerodynamic center. The shift of that with respect to an unswept wing. So yeah. And then what we see, if we just look at all the results, and these figures are not necessarily that important, I'll get into a better comparison later. But the kappa D kind of changes for, on the horizontal axis, we have increasing wing sweep, and the different shades of darkness are different aspect ratios. So the darkest are aspect ratio 20, the lightest are aspect ratio 4. And then we have these different quadrants for the different taper ratios. And so we see that the induced drag changes, obviously, for all these different wings. You see that it decreases with increasing sweep. Yeah, but we'll find a good comparison between constant sweep and linear sweep in the next few slides. So how do we compare these really? You could say we're just going to compare them at equal sweep angle, but that's not entirely fair, because if you try to picture a wing of with a constant sweep profile of 20 degrees and a linear sweep profile where the tip is swept 20 degrees, then you'll see that the crescent shape is mostly ahead of the wing with constant sweep. So it's effectively less swept. So we thought that wasn't a fair comparison. An equal lift coefficient, that's not very useful either, because we're looking at these kappa Ds, and kappa D is a term that is nearly independent of lift coefficient. So that wasn't the way to go either. So we decided to compare wings at at equal aerodynamic shift kappa AC, because kappa AC is a good measure for longitudinal stability. It's in the static margin. These if you compare two wings with similar kappa AC aerodynamic center position, those are two wings that will be used in fairly similar airplane applications. So we can plot for a particular wing kappa D versus kappa AC. So really kappa AC is a shift in aerodynamic center, but you can kind of think of it as increasing sweep. So on this horizontal axis, we have kappa AC, but as you move from left to right, the sweep increases. And the red line here is the kappa D, so the measure for induced drag for increasing sweep of a wing with a crescent sweep profile, aspect ratio 8, taper ratio 0.25. And the black line is the induced drag for a wing with constant sweep. And if you plot these, they're going to intersect at some point. And so at that point, you have two wings. I drew them here on the left that have the same aerodynamic center position and the same induced drag. So aerodynamically, these wings are identical pretty much. But you see that the tip sweep angles are different because, like I said, effectively a linear swept wing is less swept than a constant swept wing. If we look at these two lines here, the red and the black line, and we subtract them from one another, we get a delta kappa D. And the line so it's defined as the drag of the wing with linear sweep profile minus the drag of the wing with a constant sweep profile. So what that means is if that value is negative, it means that the constant sweep profile produces more drag than a crescent wing. And so the intersection between that black and red line from the previous slide is where delta kappa D is 0. And so that's this point here marked by the cross section of the dashed lines. And to the right of that point, the crescent wing produces less induced drag than a conventional wing because kappa D is negative there. But so there is a small region where constant sweep is more efficient, meaning it produces less induced drag than an equivalent linearly swept wing. And so I computed that delta kappa D for the whole range of wing designs, function of taper ratio and aspect ratio. And that's again all this data here. You're not gonna figure it out by looking at this for a few seconds. So I'm just gonna go to the next slide because that kind of sums it up. That crossover point where delta kappa D is 0, so meaning crossover point where a crescent wing becomes more aerodynamically efficient than a wing with constant sweep. You can extract that from all the data from the previous slide and make this plot that has aspect ratio on the horizontal axis, and then aerodynamics shift on the vertical axis, and then different lines for different taper ratios. And you can translate this shifts in aerodynamic center to a swept, like a sweep angle, and that's actually more useful. So the figure on the right is more easy to read. This line is the point where a crescent wing will become more aerodynamically efficient than a wing with constant sweep. So if we take a little exercise, we have a wing with taper ratio 0.25. So we're looking at the solid line of aspect ratio 10. So here on the horizontal line, and we want to sweep that in our airplane design roughly 6 degrees. 6 degrees is the point where a linearly swept wing will start generating less drag than a wing with constant sweep. So if we were to want only if we want to have less degrees of sweep, then we should stick with a constant sweep profile. If we want more sweep, then we should stick with a linearly swept profile. So the conclusions of that is we looked at a large number of wing designs. We were able to do that thanks to the low computational expense of panel methods. And there is in fact a trade-off in aerodynamic efficiency between wings with constant sweep and wings with linear sweep. So that means that Crescent wings are not necessarily always better. There is a point where a wing with constant sweep can be more efficient. And for the higher taper ratio wings, you achieve this trade-off at lower kappa AC than at low taper ratio. So I'll go back to the previous slide here for a bit. Like I said here, higher taper ratios, that's this dashed line at the bottom is taper ratio 1. And you see that the sweep angles needed to for a linearly swept sweep profile to make sense are lower than those of a low taper ratio. So really, if you have an untapered wing, anything below 4 degrees or above 4 degrees of sweep for any aspect ratio, you should go for a linear sweep profile. And if you decrease taper ratio, that crossover point moves to higher sweep angles. And I believe that is the last slide. So if you have any questions, go ahead. It's a lot to go over, so I had to pick and choose a few slides from hundreds of slides. So don't be ashamed if it doesn't make total sense.
Thanks, Bruno. Any questions? Okay, I see we also have, thanks Bruno for joining us. Like I said, he took time out of his day at DART Corporation to present this. So tell Willem, thanks again for letting you do that. I see we have Greg Rich online and John Moore. Thanks for taking the time to join us.